Welcome to the third video from chapter 5. This video talks about the central limit theorem. So the central limit theorem allows us to use statistics when our data is not normally distributed. There's a lot of notation here that I have to go through, but what I really want you to do is I want you to go to your textbook as a reference for these various different types of notation. All right, let's start with population parameters. Remember, these are numbers that describe populations. So we have the population mean, which is mu or mu sub x. Although I prefer typing, and I think more statistics should be typed like this, your textbook has some notation, so let me show you what that would look like. Mu is this one, or if I look at mu sub x, it would look like that. This is the central tendency of the random variable, the expected value of the random variable. Then we have the population standard deviation, sigma, or sigma sub x. And sigma is a Greek letter. Looks kind of like an O with a tail. Sigma or sigma sub x. And this is a measure of how spread out the random variable is around the mean. Now we have a sample of size n. So collect n observations randomly from the population. We can calculate the mean of the sample, which is different from the mean of the population. The mean of the sample goes back to chapter 2. It's descriptive statistics. It's X bar, X with a bar over it. Let's see if I have a picture. This right here is X bar. Calculated by adding all observations and dividing by the number of observations. And that's called the sample mean. We have the sample standard deviation, S. S is the English letter, or it might be Arabic, I don't know. Not Arabic, sorry, the English or the Roman letter, if that's what it is, Latin. And sigma is the Greek version. So sample standard deviation, S, calculated by summing the squared differences between observations and means, then taking the square root. If you need a reminder, go back and take a look at chapter 2. This describes how spread out the data in the sample is, not the data in the whole population. Okay. These are for numerical data. We can also look at proportions. So we have the population proportion, which is P. This refers to the proportion of the population that has the characteristic. So for example, if 70% of the population likes peanut butter, P equals 0.7. And compare that to the sample proportion, P hat. I usually write it without the hyphen, so it looks like P hat refers to the proportion of the sample that has the characteristic. For example, if I sample 100 people and 20 like spinach, the sample proportion P hat equals 0.2. And let's see if I can look at P hat. Careful with this, Google. I better pause just in case. All right, I found it. This right here is called P hat. It's P with the little caret on top of it. So when you see that, you're looking at the sample proportion. All right, so that gets us started. Now let's talk about the central limit theorem. The central limit theorem states that any random variable, take any random variable, even if it is not normally distributed, i.e. not bell-shaped. Collect a sample of size at 30 and find the sample mean. Then the sample mean will be distributed normally, i.e. bell-shaped. This allows us to use the tools of normal distributions to explore populations by using sample means. Let me show you what I mean using R. After the project resumes. All right, so suppose I have some data, and that data, if I visualize it, looks like this. Definitely not a bell-shaped distribution. It doesn't peak in the middle. In fact, there's a big gap in the middle. The tails don't get small. It's not symmetric, not a normal distribution. So I can't use the tools of normal distribution to ask things like, what's the probability that I'm greater than 18? Or what's the probability of observing something less than 4? I can't use my normal distribution calculator. But what I can do is I can take a sample of size 40. So here's a sample of size 40 from my data, from my population. And I can find out the mean of that sample. And that sample mean itself will be distributed according to a normal distribution. So let's collect 100 different samples. Each of those will have 40 observations. And for each of those samples of size 40, I'm going to calculate the sample mean. There it is. There's my list of 100 sample means, each from a different sample taken from that population. This raw data has a ton of detail, but it's highly inefficient in trying to understand it. So instead, I'll make a histogram, and all of a sudden we see that my sample means are distributed something that looks a lot more normal than the original population. And now I can use the central limit theorem to explore sample means, which will tell me about the population itself. If I want to have even more normally distributed data, I can increase my sample size. And I can increase the number of samples that I make. And I get something that looks very, very normally distributed. So I'll copy this code in so you can play around with changing the number of samples if you want. Or the size of each sample. Now, there's a lot of highly technical mathematics that goes into proving the central limit theorem, proving that it works. But actually using it is fairly simple. We use the central limit theorem to ask about sample means. So we need to know the parameters for those sample means. We know that mu sub x is the population mean for the random variable x. We define the population mean for the sample means. At this point, I'm going to be saying the word mean way more often than I want to. It can be very hard to keep track of it, but do your best and come back to your textbook or these notes to help you as you need. We define the population mean for sample means to be mu sub x bar, which you have written in your textbook. This is the mu symbol with the x bar in the subscript. And what's really nice is mu sub x bar is the exact same thing as mu sub x. Which is to say that the best guess for a sample mean is the same as the best guess for any given observation. Let's take a look. So here I have my data. And if I take the mean of my data, it's about 12.5. And here I have my sample means. And if I take the mean of my sample means, it's also about 12.5. The mean of your sample means is going to be the same as the mean of your random variable. The standard deviation is different, however. Standard deviation for the sample mean, we write it as sigma sub x bar, the sigma symbol with x bar in the subscript. Sigma sub x bar does not equal sigma sub x. It does not equal our basic standard deviation, but it's very, very close. All we have to do is we have to take our standard deviation of our variable and divide it by the sample size. The spread of the sample means is equal to the spread of the data divided by the sample size. Let's do an example. Our data had a mean of 12.5, and let's look at our standard deviation. 7.25 about. Our sample means had a mu sub x bar also of 12.5, and the sigma sub x bar, let's take a look. So let's find the standard deviation of the sample means, 0.365. I better make sure I have the right, actually, let me go back here. Okay, that's better. 1.2, 1.19. And so if I take 7.25 and divide it by the square root of the sample size, which was 40, I get something very close to 1.19. All right. At this point, I'm going to do an example from the homework to show you how to use the central limit theorem to answer questions about sample mean. All right, here we have a question from the homework. Suppose that the average number of Facebook friends is normally distributed with a mean of 141 and a standard deviation of about 44. Assume we have a sample size of 11, which is okay in this case. What is the distribution of the sample mean? That's our X bar right there. Well, for X bar, the mean is the same, it's 141, but the standard deviation of our X bar is going to be 44 divided by the square root of 11. So it's going to be 44 divided by the square root of 11, which is 13.2655. We have the same best guess, but we expect the sample means to vary a lot less because bigger sample sizes lead to better estimates. For the group of 11, find the probability that the average number of friends is more than 146. Okay, so I can come over here. So the mean of X is 141, standard deviation of X is 44. So mean of X bar was also 141. Standard deviation of X bar is 13.26. And now I want to know probability that the mean of the sample of any given sample is 146 or more. So for that, I can do p-norm. 146, the average is 141, and the standard deviation is 13.26. And let me make sure I have super accurate 6.5. And that probability is 64%. I think that was a left-tailed. I want it to be the probability that it's greater than 146, so I have to do a right-tailed, so the left-tailed should be false. Nope. P-norm, 146, 141, lower tail, not left tail. Lower dot tail equals false. There we go. 0.353128. We can find the third quartile for the average number of Facebook friends. Third, which is the 75th percentile, third quartile, which is the 75th percentile. So we do Q norm, 0.75, 141, 13.2665. Since we're doing percentiles, we want the lower tail to be true, and we get 149.94, which you would probably round to 150 because nobody has 0.9 friends. Now, notice 11 was a lot smaller than 30, which I said was the minimum sample size, but we're in luck. If the underlying distribution is also normal, then you don't need a sample size of 30. So we needed that underlying normal distribution to be 30. There we go. So there's some other questions like this. Here's one where the underlying distribution is uniformly distributed, but you've surveyed 40 people, so your sample size is large enough to use the normal distribution and to use the central limit theorem. Okay, so the key point from the central limit theorem is that we answer all the same type of questions that we answer about normal distributions, except we answer those questions about the means of samples, not the random variables themselves. And we use the mean, we use mu sub x bar and sigma sub x bar for the normal distribution calculations. All right, that brings us to the end of this video and the end of chapter 5 lecture. So I'll see you next week for chapter 6.